Welcome everyone. My name is Queen and I am excited to share my project on using machine learning to predict climate change impacts across Europe. This project involves applying advanced machine learning techniques to forecast climate-related changes, adding ClimateWins, a non-profit organization in their mission to understand and mitigate the effect of climate change. Today, agenda, we will talk about the objective and hypothesis, the data sets, some optimization methods, and supervised machine learning models we use in this project. Finally, we will talk about summary and recommendations. Now, let's start by discussing the objective and hypothesis of this project. Climate Wind is interested in leveraging machine learning to predict climate change consequences across Europe and potentially the world. We have three hypotheses. The first one is machine learning can accurately predict the increasing frequency of extreme weather events using historical weather data. The second one is that machine learning models are particularly effective for forecasting specific weather conditions. And the last one is a positive correlation between warmer, milder climates and the occurrence of pleasant weather days. Now, let's move on to the data sets used in this project. The primary data sets we use are come from the European climate assessments, featuring comprehensive weather observations from 18 stations across Europe, meticulously recorded from 1960 to 2022. We have some data challenges in using this dataset. The first one is that changes in instrumentation, measurement methods, or station locations over time could introduce variability. The second challenge is that data from 18 stations were analyzed, while data from over 26,000 stations across Europe were available, possibly leading to representational bias. Next, we look at how we optimize this data for our analysis. First, we talk about what are data optimization methods. There are various methods were employed to enhance data management, boosting efficiency, reliability, and overall utility. And in this project, we look into more what is gradient descent. This is a key technique used to find the best fit light or curve by minimizing the error, enhancing model performance. Let's now discuss how we visualize the data. We use line plots and scatter plots to visualize weather data across all stations for different years. We use scatter plots to summarize 1 year of temperature data over time. And here we have log functions to assess deviation between predicted and actual weather data. In here is the graph about gradient descent applied to pinpoint the local minimums in the datasets, optimizing the model. Moving forward, I explain the supervised machine learning models used in this project. The first model we use is KNN, which stands for K nearest neighbors. It determines the class of data point based on its neighbors. The training accuracy is about 56.83% and the accuracy for the test is about 44.72%. The individual station accuracies varies from 85.38 to 96.23%. The second model we use is the artificial neural network, which can be called an ANN, and it uses a network of interconnected nodes to compute the outputs. Here we have the results for the training set is around 99.83%, and the accuracy for the test set is around 55.6%. The individual station accuracy varies from 93 to 96.9%. And the last one, we use the decision tree models. We narrow down the solution by asking more and more specific information. The accuracies for the training set is around 60.36%, and the accuracies of the test set is around 63.56%. For the in-video station accuracies, it varies from 90.9 to 95%. Based on these findings, I now summarize the overall results and offer some recommendations. We can see that the models can accurately predict various weather events, highlighting the potential of machine learning in climate change predictions. However, the KNN model shows underfitting with low accuracy in both training and tests. The ANN model indicates overfitting with very high training accuracies but lower test accuracies. In conclusion, the decision tree model seemed to be the best performance among the models with consistent accuracy across training and tests. Finally, here are my recommendations for future work. I want to further refine the decision tree model to improve accuracies, and I want to explore sample methods to create more robust machine learning models. And the next step is to investigate unsupervised learning methods to detect anomalies in weather data. Our goal is to combine supervised and unsupervised methods to develop a comprehensive climate model that can predict both specific weather events and broader trends. Thank you for your attention, and I welcome any questions and discussions you may have.